There are a couple of special cases of logarithms. We'll talk about one of them now, and then we'll talk about the other one toward the end of the chapter. The one we're going to talk about now is the one we call the common logarithm, and that's a logarithm base 10. Probably called the common logarithm because of the fact that we work at a base 10 number system. So base 10 is our common base. As I said, typically we write this without even putting the base down. We just write log of x, and we don't even write the base. But that automatically means that we have a base of 10. And again, we call it the common logarithm. If I want to find the logarithm of 1,000, I know that automatically means the logarithm base 10 of 1,000. So what I'm really asking is, if the base is 10, what exponent do I have to use to get to 1,000? Well, I know 1,000 is 10 times 10 times 10, or 10 cubed. So the exponent would be 3, which then is the value of the logarithm. All right, what about the log of 0.01? First of all, again, when it doesn't specify, I know it's automatically a base of 10. And I'm going to make a suggestion to us here. Instead of writing that as the decimal, 1/100th, let's write that as the fraction, 1/100th. It, of course, means the same thing, but it's going to be easier for me now when I think, okay, 10 to what power gives me 1/100th, to recognize that because I had to move it to the denominator, it's going to be a negative exponent. I also know 10 squared is 100. So that'll be 10 to the negative 2. All right, this third one, the log of 23, is really the log base 10 of 23. And so I'm asking 10 to what power gives me 23. Clearly that does not come out evenly. 10 to the first would be 10, and 10 squared would be 100. So it's somewhere between 1 and 2. But I can't tell exactly what it is. And so at this point I am going to turn to my calculator. And you do have a logarithm key. It's right over here next to the 7. That will automatically be a logarithm base 10 when you use it. So I can say the log of 23, and there it is, that big giant number. It's approximately 1.3617. But it actually goes on forever. That decimal doesn't end and it doesn't repeat. It's what we call an irrational number. And so the best I can do is give an approximation. I mentioned that your calculator is capable of doing other logarithms as well. And I don't recommend getting in the habit right away of using the calculator to find logarithms when they can be found by hand, because you never really develop that sixth sense about logarithms, or that ability to sort of understand what they are. However, if you're stuck, or if you have a logarithm with another base that doesn't come out evenly like this one, you actually can find in your Maths menu if you go down a ways, you will find log base. And at that point, if I wanted to go back and check one of these other problems, like for example, back here, we had this one, the log base 5 of 1/25. Notice it does give me the answer of -2. So it's in there if you get stuck. But again, I can't emphasize enough that in order to get comfortable with logarithms, you got to do them. And so don't get in the habit of turning to your calculator right away. Try doing these by hand as much as possible so that you get used to them. All right, so let's talk about a few properties. I want to start by asking myself the question, What numbers can act as the base of a logarithm function? Log base b of x. What can be that base? Turns out the base can actually be anything bigger than 0. The reason that we never want to use a negative base, so why can't b be negative? If b were a negative number, let's just say for a moment I said the log base negative 2 of x. And then let's say I tried to find the log base negative 2 of 1/2. Oops, sorry, of 1/2, not equal 1/2. What I'd be saying is negative 2 to what power gives me positive 1/2. Okay. Well, I know to put this in the denominator, I'd have a negative exponent, but it's actually 2 to the first power. And a negative number to an odd power stays negative. So that would still be negative 1/2, not positive 1/2. And so this actually doesn't work. There are other reasons as well, but that's one good reason why we really can't have a negative base on our logarithm. It's just not able to be evaluated in many cases. So we'll always use positive bases on our logarithms. Now what about what numbers can be in the argument of the logarithm function? What numbers can we take the logarithm of? Here again, it turns out that we can only take the logarithm of positive numbers. And if you were to ask yourself the question, why? Let's just go ahead and pick a positive base, like 2. And let's say I wanted to take the log base 2 of negative 4, a negative x value. Well, we would be saying 2 to what power gives me negative 4. That certainly isn't any positive exponent that will work. And if I were to put a negative exponent in there, it wouldn't make the 4 negative, it would put it in the denominator. So there's no solution to this. It's actually not possible to find the log base 2 of negative 4, or any other negative number for that matter. We can actually go back one step and remind ourselves what we saw in the graphs. Exponential functions are always positive. They entirely lie above the x-axis. So I'll never get a negative value out of an exponential function. When we drew the inverse, the logarithm function, notice that all of the x values ended up staying on the right-hand side of the y-axis. They were all positive x values. So we really saw it way back with the graph that we were only going to have positive x values here. We'll be looking at graphs of logarithm functions in the next section, and we're going to come back to that idea that x is greater than 0, because of course what we're really talking about right now is the domain. All right, a few more properties. For any allowable base, so we're assuming now that we have a positive base, what is the logarithm base b of 1? So with any base b, we'd like to know what exponent gives a result of 1. Since we know that any base b to the 0 power is 1. That missing exponent has to be a 0, and that's the value of my logarithm. So we don't even have to know b to know that. Again, assuming an allowable base, what's the log base b of b? Or in other words, b to what power gives us b? Well, certainly b to the first power is b. So the exponent would be 1, and the value of the logarithm is 1. Our last little property, the logarithm base b of b to the n power. We have b raised to what power is equal to b to the n. That almost seems like we've answered the question right in the question, because obviously the exponent I have to put in there is n to make it match that side. So that logarithm is simply n. Once again, we'll be talking about this more as we go on, but this fits right in with our definition of inverse functions, right? The logarithm base b and the exponential function base b are inverses. So it's actually not at all surprising here that what I really have is a logarithm function and an exponential function the exponential function has been put into the log function, so this is a composition. And anytime I take the composition of inverse functions, I just get back what I started with, which would just be the n. So this is a perfect example of inverse functions acting on one another. In general, we often say logarithm and exponential are inverses. They essentially, one does something, one undoes it, and we end up just with the n value. All right. Using these properties, we should be able to answer these questions fairly quickly. The log base 6 of 1. 6 to what power is 1? Well, that would be the 0 power. Log base 5 of negative 25. We know we must have a positive argument, so there's no solution. Or at least no real valued solution. 4 to what power is 4? That's going to be the first power. And, log base 16 of 0. Again, we must have a positive. It can't even be 0. It has to be a positive number in the argument. So once again, I'm going to say no solution here. And on both of these, x must be strictly greater than 0. You must have a positive argument for your logarithm. All right, number 5. I have a base of 7, and I can either think 7 to what power is equal to 7 to the 8th power. Obviously, I'd have to put an 8 in there. Or alternatively, I can think that logarithm base 7 and the exponential base 7 are really inverses. And so I'm going to get back the 8 that I started with. Finally, the logarithm base 2 of 1. 2 to what power is 1? That would have to be the 0 power. All right, so there's our introduction to logarithms. In our next section, we'll start looking a little bit more at graphs and also some applications of logarithms.